First, we will solve one question and then we'll go to natural sampling. So in this question, it is given that a signal x of t is equal to 2 cos 400 pi t plus 6 cos 640 pi t is ideally sampled at 500 Hz. The sample signal is passed through an ideal low-pass filter with cutoff frequency of 400 Hz. Sketch spectrum of sample wave. State what components will appear at the output of the filter. So this is the equation that is given, and whenever the equation is given, we have to first find the frequencies. The frequency from this component will be 200 and from this cosine component will be 320 hertz. After that, whichever is highest, that will be our fm. So fm is 320 hertz. Now from the sampling theorem, we know that fs is equal to 2fm for Nyquist. So it will be the max, the least frequency that can be used for properly reconstructing a wave is 640 hertz. Now this is what we have found. Now we have to convert the whole thing into frequency domain. So whenever cost term is given, the cost, this is how it will be in the frequency domain. We have already solved one of the example using the whole thing, like how this thing appears in the previous problem. Like this is done using Euler's form, and you can just directly write it. If there is a cost term, you'll get to know that one term will be in at 200 and another will be at minus 200, and there will be an extra half amplitude, and same goes for cos 640 pi t. After that, you have to write it, combine it and write it in the form of x of f. So our equation was what? X of t 2 cos 400 pi t plus 6 cos 640 pi t. In the place of x of t, now we want x of f. So we have to, wherever there was constant, we are converting it to frequency term and writing it. So once we do that, this is what we will get, and after getting it, we know that one term is at 200, another is at minus 200, and 320 and minus 320. But here you can notice that the amplitude here is 3, but here the amplitude is 1. That is why there is a difference in the spectrum while drawing for the amplitudes. After that, now this is what was the original wave that was given. Now we have to draw the sample wave. To draw the sample wave, uh, we from the original wave, first we have to draw the original wave at minus 200, 200, 320 and minus 320. After that, we found that our fs was what? Our fs was 640 hertz. So we have to draw a line around. Our fs was 640, but it in the question it is given as it's sampled at 500 hertz. That is undersampled, and so at 500 um, you have to draw all the spectrums relate around the 500. Like if you can't do it directly, you can just do it using these terms. Like you can just use this 8 forms for one sample. So f minus fs, f plus fs, and so on, and you can just calculate, and in those particular samples you can draw the spectrum, and this will be your final answer. And the other part of the question is, what components will appear at the output of the filter? What components will appear at the output of the filter? And the cutoff was 400 hertz. Since the cutoff is 400 hertz here, when we have drawn the spectrum, now 400 will be somewhere here, right? Before 500. So from here to somewhere here. So you have to state what and all components are there. So you have to state like a component at 200, minus 200, minus 320 will appear at the output after after it is filtered. So now let's go on to natural sampling. So what is natural sampling? It's everything is same except that in the previous examples we had seen, or in the previous videos we had seen, that sampling is done using impulse train, right? But in actual, there will be no impulse train. This is an ideal condition. Instead, this impulse train will have some width, and so this is the practical thing that is possible. So instead of taking an ideal train, if we use a pulse of train, then it is called as natural sampling. So let this be one pulse. So let it vary from minus tau by 2 to tau by 2. We can then write it in a mathematical equation as pt of t is equal to k varying from minus infinity to infinity p of t minus kts. So if k is 0, it will be p of t. If k is 1, it will be p of t minus ts. So basically indicating that one pulse is at 0, one another is at ts, another is at minus ts, and so on. Okay, so if we want a message signal and if we want to reconstruct it, we can do it using impulse trains like this. So if I'm having a train like a message signal and I'm using a pulse of train, I'm just, this is what I'm doing. Now I can easily make out this is the waveform structure, and it can be easily reconstructed if I have only these pulses. So that is the idea behind natural sampling. And um, here is the mathematical derivation for it. Okay, so it's everything is same. First, in every derivation, first you have to just go for Fourier series, because it's same as the derivation that we had solved for ideal pulse train, but just the here the width will be included. So since it is periodic, it is varying with the period ts. We will use Fourier series, and we know that the formula pts of t will be, this is the formula for Fourier series. Now in the previous derivation we had used dn as our coefficient, but here we are using pn, so that's the only difference. And there our pulse was varying from ts by 2 to ts minus ts by 2 to ts by 2, but since here the pulse has a width of minus tau by 2 to tau by 2, it is varying from minus tau by 2 to plus tau by 2, and this is the thing we get. And once we substitute p of n in this and solve, if now we will solve for p of n so that we can substitute it later here. So let us assume that this is I of ts, and uh, and the amplitude of pt of s of t is 1. So if we substitute 1 here and we keep on solving, so when we solve it, when we integrate it, this is what we get, e power minus j 2 pi n tau s. Since we are integrating with respect to t, all the remaining terms will be in the denominator, and since we are integrating over minus tau by 2 to tau by 2, this is how we write it. And after that we will just substitute for t. It will be 1 by ts by 1 minus by 1 minus j 2 by n by ts. When we substitute for tau by 2 in this, it will be e power j 2 by n tau by ts by 2 minus of e power minus j 2 by n 2 by tau s. So after simplifying all of this, you will get this term. Okay, and from Euler's form, you know that whenever it is e j theta minus e power minus j theta by 2j, this will equate to sine theta. Alright. So what happens is, now we know that theta, this is our theta, and this is our 2j that we need in the formula. So we can separate pi by n here, and minus will remain, and this can be basically written as what, sine. So this is done. Now since we know that whenever there is a term like this, it is equal to a sinc function. So this will be like equal to sinc function, right? So what happens is, I will try to uh, since I have all the terms, I have pi by n, but I don't have tau by ts here. So what I'll do is I'll multiply it by tau by ts and divide it by 2 by tau. So basically I'm just trying to create a form here. So when I do that, it will be pt of t n is equal to minus infinity to infinity tau by ts sine pi n tau by ts and all. And this is what this we got sorry, we got this for pn, and now we are substituting it back in pt pt of st here in this equation. When you substitute this in this is what you get. Okay, so now we know that this is the extra term that we got. Now further solving it, now ms of t will be m of t pt of t. So when I substitute in this and I solve for it, this is why do I need to do this is I have to find my message signal. So message signal will be what, m of t into pt of t. So whenever I have reached till this point, this is not the end. I have to convert it into frequency domain also. To convert it to frequency domain, we know we have to do Fourier transform. To do the Fourier transform, this is the formula that we have. So now I will substitute in this for ms of t. So here I had got ms of t. So this thing I'll substitute here. So after substituting, this is what I'll get. Okay, I'm just writing it all over again, that's all. This is not simplified or anything. So after that, what I'll do is I will interchange the integration and the what is that, summation. So summation and this whole term I'll take it this side, and this integration I'll take it this side, and here I'll write this all together. Okay, so now I know that this whole term is what, this whole term here I have, one I have is fs and another is f. So it will be f minus n fs because here I have extra. So when I join them and if I write, this will be m of n minus m of f minus n fs. Okay, so this is the frequency domain thing I got. Okay, and if this is my signal, original signal, then this will be my reconstructed signal. In the previous examples, like in the ideal cases we had seen, the sample was always straight, so like the amplitude was normal. But here you can see the amplitude is varying because this is a sinc function that we got in the equation. So sinc function is what, sinc function goes like this on the both sides till infinity. So here it will go like this, and so with that our samples will vary with the amplitude. So this is the practical case that actually happens, and this that we did in the previous examples was for the ideal case, and that's natural sampling. Thank you.